Hello, everyone. Let's do this. Let's talk about crypto-polyglots. So, crypto-polyglots, what's that? Was that? Sorry, just forgot to log this. Okay, crypto-polyglots. Welcome, everyone. Feel free to drop questions if you want. And live chat. Yes. Okay. Yeah. So, crypto-polyglots. To remind you, if you haven't seen previous streams, is that so? First things is that okay. So this is again, look at my this is one of my streams or live streams. So if you're not familiar with the topic, you may definitely want to look at I introduce various file formats, then the first polyglots made by hand, polyglot being a file valid with several file types at the same time in the same file. Then what would be interesting, Mitra, weird files and Mitra for stream 17. And yeah, the rest is not so important, but definitely, again, depending on your level of skills, PNG, PDF, and zip, I introduced them previously in other streams. So PDF basics, PDF parasites to understand how. I mean, if you want to know all the details, basically. But basically, I presented all the details you might need to know for this topic until now. And so in my Mitra slides, that's my Mitra slides. All the slides are available on speaker deck on my speaker deck /Ange. And basically, we have polyglots that and Mitra is able to generate polyglots. And then you have the overlaps of signatures at the same offset is preventing some file types to coexist in the same file, because, for example, there's no PNG BMP polyglot because they both start at offset 0 with different signatures. So basically, there cannot be a valid polyglot of a PNG BMP of the two file types at the same time. So near polyglots are non-working polyglots with data to be replaced. So basically, almost a polyglot, except that there will be an extra data. It's like a polyglot, but there will be some extra data that will be. You may not see it in the string in the preview of the video. I'm seeing that now. This is not practical. So basically, you see there is as if it was a polyglot, and there is some overlapping data that is kept. And when you replace this data, then you change the file type. You change the content of the file, obviously, but you re-enable some extra content. So basically, it's like splitting the file. And then, are they useful? Then they enable some tricks. And then if you replace the swap of the overlap, you'll do it via cryptographic operations. I call that a crypto-polyglot. So this is a PNG BMP file, as I mentioned. And as you can see, they both have different magic. So BM and PNG, all this is the magic in the case of PNG. And basically, you cannot, you will swap, the file will become valid PMB or valid PNG because the first line, the first block of the data, depending on which side it is, then will enable the other file type. Okay? And so that's it for polyglots, near polyglots and crypto-polyglots. And basically, they are interesting because they are a bit out of this world, as in file formats. They are very definitely not functional. Not standard files that you come up with easily. And both the case of crypto-polyglots that I'm going to mention are from the need, from two perspective of, is it possible to do this? And it looks like it isn't from a cryptographer perspective. and file format tricks and crypto-polyglots come at to the rescue to actually help making it possible. In the case of the first one that I'm going to present is I was challenged by Meowbiz to make a JPEG that is valid after being encrypted. So a JPEG that is still a JPEG. And then I reach out to Jean-Philippe Masson because I'm very bad with crypto. And I was like, is there a possibility to control the output after decryption? And he told me the short answer is yes. For example, only a small thing, but that was good enough. The initialization vector in the CBC mode. So we'll see what it's about. So very important concept, and that was new to me at the time. It was like 10 years ago or so. An encrypted file is not always run encrypted, as in the result of encrypting a file, even with the standard algorithm, is not always the random looking of a file. And here the thing is, the concept is that the result of encryption of a file, even via standard encryption, can be valid. Okay, so how is that possible? So let's do it very simply. We have two formats, very simple format. A data format that contains some data and that has an end marker, which means everything that is after the end marker will be ignored. And then another format that is, let's say, a text. It has a magic. And this is a text, okay, pure text. So we see that these formats, they cannot coexist because of the data and text magic. They are hypothetical format, but that makes things simpler. And the data format tolerates append the data after its end marker. And the text accept comments between the usual it's command syntax, as in parasite in the host. So let's imagine, yeah, Meowbiz, that you're right, Levon. That was his. Where is it? But no, it's Meowbiz is a Finnish, so I'm not sure what. I actually don't know what it means. I hope it's not offensive or anything. So let's take two hypothetical format to make it simpler. One, both having the magic at offset 0. One that starts like it means bad word. Oh, I'm sorry. That's his fault. This tweet was 10 years ago or more. And though if we encrypt, we get random result. If you encrypt clear data, then you don't control the output. You cannot control the output and input together. But AES works with blocks. So file encryption is applying AES, but via a mode of operation. So when you, for example, when you use the ECB mode, you know that every block will be encrypted independently. So basically, every two identical block will encrypt to the same thing, which is why in the case of a raw image, you can clearly see the colors have been changed more or less, but each 16 blocks are identical 16 blocks are encrypting to the same result, which is why we use different modes. And one standard mode is the CBC mode, cipher blocks chaining, where you have an initialization vector that is used, and it is used to be XORed with the first plaintext block, and then this is encrypted with AES. You obtain the first ciphertext block, and the ciphertext block is used to XOR on the second plaintext block. So basically, there's a chain of the result of the ciphertext is used on this next plaintext block, and so on. So basically, even if P1 equal to P2, then the result will be different. The C1 will be different from C2 because the XOR will have a different impact. And the fact that all cipher blocks will be different, it's impacting the next block too. And basically, we can revert all these operations. So if we instead, so C1 is the result of encryption after XORing with the initialization vector. So basically, the initialization vector is the XOR of the first block of plaintext with the decryption of the first ciphertext block. So basically, we can manipulate if we have given C1 a ciphertext and if a valid P1, we have a way with a given initialization vector to get this operation possible with AES. So we only control the first ciphertext block, but that's good. That couldn't be good enough. In the case of our example, so we encrypt with the pure AES, and then we determine the IV, as we saw, to control the output of the text block. So now the rest will be random. We don't control the rest. I mean, with random, like and not out of control, because we want to control the next blocks of the plain text. So therefore, the next blocks of ciphertext will be out of control of the initialization vector. Now, what if we modify this even a bit slightly? Now we modify you saw that it's XOR, right? What if we just encode a comment, the start of a comment? So we make the text file format ignore the rest that is random looking. And now after this random, we can add something that will close the comment, and then there are data. And this file is equivalent to the initial file because there is a text signature, there's a declaration of a comment, there is some stuff that is ignored, there is the end of the comment, and there is our initial data. So this file is equivalent to our initial text data. Now we can actually decrypt that file, this outcome, and this will give us the original file with some pre-decrypted ignore random, but also the rest of the pre-decrypted valid data. And AES-CBC only depends on previous blocks. Whatever we happened guarantees that the previous blocks will still work the same. So this data file will indeed decrypt to a text file. So basically, these are the structures of both sides of the file. I mean, before encryption and after decryption. And since encryption is just a symmetrical operation from decryption, then you can do that with actually more modes, and you can do that with even the other way around, which is also why, where is it? In one of my files, I did that in more ways. Let's put it that way. So, for example, you just take this very small example and you run it without given a encryption key and the IV that was computed that way. And this is the valid. This is a file that works by hand. You can even do that at scale. So here was a JPEG picture that when you encrypt it with AES is a PNG picture. And when you decrypt the same file with triple des, because again, it doesn't work just with AES and it doesn't work just with the CBC mode, then you could get a PDF document. And if you encrypt it again with a different key, and it also depends on the key, then you get a flash video. So as you see, I did it's the same file, right? Is the hash available? This one. Let's see. Where's total? It should be on VirusTotal. Yeah. Okay. No question. So this file, yes, exists 9 years ago. Okay. So what did I do with that? Well, Mitra is able to, no, this is not the right window, sorry. So Mitra is indeed able to not only generate crypto-polyglots, so you just give the input file and with the overlap parameter, and we will store this using a very specific syntax where O means there is an overlap, then 10 and 40 means the offset where the content is changing side. and you can see that 10 and 40 matches the moment where the color changes. The file types, because why not, with the original extensions. And then that's the content to be replaced. So this is the BMP header in the file that it gave you. So it will give you automatically this file. And now I created extra script in Mitra util. So Mitra direct, my Mitra, yeah, directory. I don't have the Mitra repo open. So you have utilities, and I create a few with the different modes. So encryption, no need of overlap for ECB, and with overlap via IV, it works with CBC, CFB, and OFB mode. So then with Mitra, it's instant to create these files automatically, and also to just generate this construct with the key that you want. Now, okay, this is another example, very interesting because also very compact with PostScript, which only needs 3 bytes as a kind of magic. It's a bit special PostScript, even though it's a text language. If you generate, this means maybe it's actually 2. This is weird. Maybe it's actually 2. So this generate a function, like a bit like in PDF, but with no name here, and it's valid. And then this is the body of the function between the curly brackets, and it creates a script string, and the string between the brackets, the parentheses, is ignored as long as the content is balanced properly. It's a bit like PDF, basically, even though PostScript is older. So basically, this means, oh, this is an empty function that just contains a string, and as long as this function is not called, then it's fine. So basically, this adds like a super comment as long as the parentheses are balanced. And Mitra is again able to do this automatically. This is a PostScript file, the original one, and it will generate the files directly. Okay, no questions? And so now we covered what was called AngeCryption. Did I even? Yeah. So basically, that you get the idea. AngeCryption doesn't have so much practical use. As far as I know, it's only very rarely that you can control the IV. But again, it was the first one. At the time, I didn't have this whole notion of I didn't have this whole notion of near polyglots and crypto-polyglots. I didn't think there would be a generalization of crypto-polyglots. And it's Janssen who decided I was looking for an actual scientific name, and he coined that AngeCryption. So here we're done for AngeCryption, and the next technique is quite different in history. I mean, the way it works. And what I didn't know was that, so again, it was known that from the beginning that you could control the I mean that IV would give you some control of the first cipher block, and no one thought that there could be any security risk out of it. Axel April, she although we worked on some slides together, she presented at Black Hat Europe, if I recall correctly, and basically creating a DEX file Android app that would also decrypt to something else. I mean, basically combining a DEX and an inner image to have a malicious APK that is hidden in image just via a single operation of encryption. So again, because it's the next payload is under encryption, it's very well hidden. It's like there's no risk of detection of that. There is a risk of detection that the file is weird. We have just some advanced scanning, but definitely not the case of the two payloads are valid at the same time, like identical prefix collision. Now, With TimeCryption, the next one is it's a bit different in the way it was born. And in 2019, there was this paper. Don't know if you can see properly, with a cryptic title that was presented at where was it presented? Fast message franking, presented at Crypto 2018. Sorry, the paper is from last version 2019. And basically, under this cryptic paper, let's haha, there was a vulnerability in Facebook Messenger via ASGCM. So at the time, I had no idea what ASGCM was, and it's my colleague Daniel Bleichenbacher who was looking for me, because with this paper in his hand and claiming that this paper was interesting because it has a picture of cats. It was very unexpected to see Daniel say that. And basically, he starts to talk to me in very cryptic ways. So basically, he about ASGCM, and my knowledge of cryptography was not good enough. Even the way that Daniel was talking, he was saying, for example, the file starts with a differential, and I didn't know what it means, but it just means that the files are different. So, but I never heard that myself before. I'm not a cryptographer. And a huge thanks to Stefan Kölbl, my colleague, who was there, but also who was able to understand, to take all the time. We spent at least 9 hours explaining to me the details of what was possible, what was not possible with, and what was ASGCM, what was the restrictions, and so on. And basically, it was a surprise, because ASGCM just meant to me being a standard in authenticated encryption, and there's no way it could be vulnerable for anything because it's standard, right? But it turns out that you can very easily craft a ciphertext that will work with two different keys, and that was known from the very beginning mathematically by cryptographers, and not for non-cryptographers, let's put it that way, but it was ignored by cryptographers because it was perceived as not vulnerable. And this paper, the fast franking one, the fast message franking one, dealt with BMP and PNG, because as you saw earlier, a BMP has only 2 bytes of magic, so it's a bit easy to abuse. And then we actually made a paper to Usenix much later that was generic over many formats because it's based on Mitra. So we'll see what it's about. So a lot of people were actually vulnerable, and now there are lots of suggestions about GCM being replaced, and even our paper suggests how to abuse and also fix authenticated encryption with key commitment. So key commitment means making sure that only one key can be used. So even some stuff was subscribed with Google was internally vulnerable to GCM lack of key commitment, which means, oh, there could be different keys. It can be decrypted. Stuff can be crafted so that it works with different keys, and that makes the whole thing malicious. And even Amazon SDK was vulnerable. So yeah. So that's the thing, right? Is GCM broken? Oh, did I fix some? Okay, so let's go back a bit. Let's go back a bit before we speak about GCM, actually. So GCM works different from the other mode. I mean, from the other mode. It's a needs a used once number, so a nonce, and from these nonce and the key, it will generate a key stream. And the key, the nonce, is just concatenated to a counter, and the counter is updated for each block, and this way several blocks are created. And these blocks create a key stream, and the ciphertext ends up being XORed with that key stream. I mean, the ciphertext is a XOR of this key stream and the plain text. So basically it makes the whole AES work, the whole encryption block algorithm work as a stream encryption, and is just XOR against a key stream, which is generated via nonce and, of course, with a given key, nonce and the counter that is updated. And that way it acts as a one-type add, like a XOR with a random stream, which is supposed to be, like, has good specifically interesting properties. So basically, you generate, via encryption itself, a long key, a key stream, the length of your plain text, and you end up XORing that. So the nonce and counters is the source of the encryption. The block cipher is used to generate a key stream that is independent of the plain text and ciphertext. So basically, you can already generate all this in parallel, and even say, oh, I know what the plain text to be encrypted will be for the block 1000. So TTR counter mode is just XOR with a key stream. And the decryption and encryption, because it's just XOR, are the same operation. It turns a block cipher into a stream cipher. The actual decryption of the cipher is not used at all, just to generate the key stream. The decryption is the same as the encryption, XOR with that key stream. So what happens if we decrypt with a different key? We just end up XORing with a different key stream. So the idea would be craft a ciphertext that gives meaningful plain text for different key streams, something that is ambiguous, that could have two meanings. So you do your operation, you generate a key streams in some ranges of the stream that are interesting, and you do that again with a different key, and then you combine that like cutting two sausages, a Nuremberger and a Frankfurter, and and mixing them together. And then you take this combined ciphertext and you decrypt that, and you will end up with the green content, which should be what you wanted, and the other one will be different. So you make two valid contents coexist by encrypting with different key streams and slicing on the given offset of importance. So what about craft ciphertext? There's nothing that prevents us to modify the ciphertext. The key stream is set by the nonce and the key. The plain text and the ciphertext are involved. So for a given key stream, if we change ciphertext byte, we set the plain text bytes. So if the key stream is set by nonce and key, then we can say, oh, these key streams are set because of the keys and the IV counter, but and the index of the block. So whatever you modify, you will get the XOR via the key of that. We XOR with the key stream. So now you can see the generalization of crypto-polyglots, on polyglots at least, several valid contents in the same file. Yeah, that's binary polyglots. And this is where Mitra can be also helpful. And that's Mitra. Okay, Mitra. So again, you generate a polyglot with Mitra. So here's an example of a polyglot of a JZip and a RAR. Oops. And you have a limit, and Mitra will actually just do that. S means stack, and that's the offset where the content is changing side again. And there's a tool for Mitra that will just take that and generate the final file, and it'll even give you the parameters to generate the two files from the output with just a different key. And you can, of course, set your key, and in this case, there is no initialization vector or whatever. And you will get, again, with the first key or the second key from the same ciphertext, you will get either your original raw files with some garbage before, or your original JZip file with some garbage after. So it's not just polyglots, it's two related files coming from the same ciphertext, and one format is hidden when the other is in clear, which hides the malicious payload and would bypass anything like polyglot blacklisting. Before your R signature, there is no valid signature to be identified. So that works, even though there is trailing garbage ignore, just a small warning. But I did this example here because it's also very compact. These two file archives are creating standard files. Now, I only spoke about CTR because GCM is kind of upgrade on CTR. So let's do it step by step. And now you do not want an authenticated encryption because again, you have a lot of possibilities of attack. And again, if you could change freely the key, yeah, you are at risk. So you want to use authenticated encryption, which is considered more secure. GCM is the Galois counter mode, and okay, there are other modes. That's yeah, and now it's basically CTR. There is a pre-auth part that doesn't depend on the plain text and ciphertext. That can be just works on the authentication data, and then there is an authentication that works in parallel of the decryption. And the new inputs are there is authenticated data. So basically, you want to authenticate according to something that corresponds, for example, to a description of the data that you want to encrypt. And you also have a tag that will be used to validate that when you decrypt your ciphertext with a given key, the tag will have to match. So basically, a small way to prove that you're using the right key. The authentication tag depends on the authentication data, the ciphertext, the key, and the nonce. And basically, on the encryption, you recompute it and you compare it. So GCM mode, it's using CTR for encryption, and there is a function ghash. And yeah, that's about it. So basically, now it's a more simplified version of it with the whole authentication operation for the whole authentication data and the result of decryption all chained together. That creates the authentication tag. So we can't use a different key, and most non-cryptographers thought you can't because that's authenticated decryption. So what would be the point if we can use a different key? And no, you can actually make it so you can force stuff so that two decryptions with different keys, they both pass verification. And it's not a lot of it's not a lot of computation. You can even cache the result. I mean, whatever it takes like a minute in a badly done way. But it was known for a beginning because it was not seen as a risk. Because so what? You can have two different keys, but what's the impact of that? Okay, there are failures in the wild. And again, the property we exploit does not violate any security goals of authenticated encryption. It's not it's not a property that you expect. So now the thing is, some systems with key rotations, they just try all the keys of the keyring until decryption is authenticated. So basically, every now and then, there is no standard for key rotations. That's the thing. We couldn't attack one because there is no such a thing as a standard for that. Otherwise, if there was and it was vulnerable, that would have hit a lot of targets. I mean, if it was a standard one. So basically, you have a system that, for example, encrypt your file on upload to store them encrypted, and regularly there's a key rotation, a new key being generated added to the keyring, and when it's time to decrypt the content, the system will just try all the keys until a decryption is authenticated. Like, oh, the tag says this is the right key. Here serve the output of decryption. What could be wrong? So if you can abuse the key generation algorithm, you can craft a tag that will be valid now for one key, and also in the future with a different key. And the new key will just be silently used by design. So basically, if you want a PDF I can send you the PDF you want, and if I know the key generation algorithm and the rotation, I mean, the key rotation and generation and rotation algorithm, then I could have something that you store to your system. I upload the file, you download it. It was stored encrypted in transit on the cloud. But later you want to download this file again, and the cloud systems added a new key to the keyring, and this payload that is indeed what you wanted to have is now something that I control. It could be totally malicious, like I could send you these slides, and also later it will decrypt as WannaCry executable. So what you want now, what you want later, and you control both. So this is why it's called TimeCryption, because it's like you can control the present, you can control the future, and it's not a bug. So, of course, Mitra has the ability to do that. And there are tools for util GCM, and it will craft a collision with some caching. So there are the tools. We call it meringue. And if you never used, so this is the overall algorithm. It's implemented in Mitra. So we implement it in two ways. It's in Mitra, in the tools, so GCM, so TimeCryption. Oh, I needed so with authentication, so and without authentication for CTR or FB, okay, the stuff we presented earlier, and then with tag correction. And this is all I implemented here in Python, because it's at the limit of the script for Python, because it's not the nicest Python. It's I mean, you will see what I mean. But and also I stored some nonces that were pre-calculated so that you can reproduce the result faster. And it's also good to store them. Oh no, that's the nonce. Sorry, that's another thing. And also the inverts. The tag, the inverts are done to store, to craft the tag working with two different keys. Not the tag, actually, the extra block that you need to modify in the file. So basically, I'm already stored some data that helps, so that our experience were more easier to reproduce. Because after all, I use that a lot, and it was interesting to save time. And also, where is it? Then Stefan did that, but in Sage. I'm not sure if you're familiar with Sage, but Sage is more basically a kind of Python on steroid for crypto stuff. So you have new definitions, and that enables you to do some more complex crypto calculation directly in the code. Even though, so it's almost Python, but it's enabling, finite fill. You don't need to re-implement that yourself. It makes the stuff much more compact. Okay, so we actually did scripts that in Sage that also take the same binary structure, with the weird naming that we use in Mitra. So basically, Mitra and Sage was able to generate the same. So here, this is the same implementation of the GCM algorithm in Sage instead of Python, but it's just that the computation will be just easier, because you just need to do it the Sage way, and not re-implement a lot of stuff yourself in Python. And so basically, you can just run that with the tool, and it needs to. And here it says already computed, because it was likely already stored. I mean, it was cached by the system. If not, it will compute it, takes a minute, and then store it for the next experiment if you want. And that works. And it decrypts authentically in both ways. But OpenSSH doesn't have a GCM decryption, authenticated decryption standard. So you can simulate this with CTR, but you will not verify that the decryption works. But yeah, of course, we provided script to do so. Oh yeah, our paper. Where is it? Our paper had all the artifacts evaluated, functional, available, functional, reproduced, and even this file, or maybe not that one, but the one on E on no, that's the Usenix one, and this one, if you see the page of artifacts, if you apply OpenSSH on this file, it will work. So this file is actually a proof of concept itself that you can so you run two times OpenSSH on this file, and you will get a PDF viewer executable through Mitra as usual, because that's the one I prefer. It's a single executable PDF viewer, so without an install, it's pretty handy. So what else? What do you want to say? So we implemented more algorithms in Sage. Where are my slides? Here, TimeCryption, okay. And you can run that with other files, with other file types, so a GIF, DCOM, a PDF executable. Again, if they both have the signature at offset 0, then it wouldn't be working. So PDF to text. Oh yeah, and of course, do I need to? Yeah, of course, you also have examples ready to use of a lot of file formats. Even sometimes weird file formats that are a bit tricky, that I had to handmade zipper, for example, for whatever reason, just to make sure. For example, in the case of PostScript, when you want to put garbage, you have to be lucky that there is no bracket parenthesis that is encoded via the encryption that is generated by an encryption. So examples files are available, source file are available in Python and in JPEG, and in Python and in Sage. Sorry, what I'm saying. And now what can be done? So decom P. So far, each such ciphertext bytes belong to strictly one payload. Can we control two outputs at once? So we know that ciphertext is the result of the same ciphertext will be the result of encryption, of XORing of the one side, one payload, and the key stream, the first key stream, and the same the other side. Now, if we want to control some bytes of both P1 and P2, we need to control we need that the P1 XOR P2 is equivalent to the XOR of the key streams for these offsets. We know that the key streams depend on the key, the nonce, and the counter. And here, what we can control is the nonce, if we can, to get the right XOR value for both keys, which enables us crypto-polyglots with two formats starting at offset 0. And of course, the smaller one of the format required magic, the better. And we can also do both formats can be the same but with different contents, which is what I provided in the example directory. Standard polyglots, standard, then with a brute force nonce of 1 byte, 2 bytes, 4 bytes, and in this case, and 5 bytes, and even ambiguous file, a file that will decrypt with two different keys as PDFs, both being PDFs but with different content, or JPEG and JPEG, and so on. Some of these files were adjusted manually, but most were still generated mostly automatically with Mitra, thankfully. And now, sorry. So the nonce file, the nonce script is just doing exactly what you expect. It will brute force and give you a value, several values. So, for example, if you just want an MZ signature to overlap with the PDF, and you just want basically the XOR of the key streams to have the value of %p XOR XOR MZ. I mean, after encryption of each key, then these nonce will be valid. For example, a valid value for that, and then you can reuse it to generate your file. So it's fully generic and it works with most standard files, which is exactly why our paper is not just a CTR crypto-polyglot, but actually a GCM crypto-polyglots. And we even put some jokes, if I recall correctly, in the parameters of decryption. Or maybe it's at the end. I'll let you check the document. Yeah, what could be these values, the keys, and what could be this authenticated data? Yeah, maybe we put jokes, maybe, or hidden messages, not so hidden now. So recapping or generating overlapping polyglots, you will need overlap in Mitra. Disable by default because I'm not sure people would expect that to happen in a normal way. And the overlapping data is staved in these curly brackets in the file names. And the longer the overlap is, the longer it takes to brute force, so the smaller, the better. We can actually do more than just polyglots. For example, dual JPEG pair. And there is a little interesting trick that happens in this case. A JPEG signature is 2 bytes, FFD8. Then there is a comment declaration, FFFE, and then there is comment length. So we need this to be valid. We need this to be valid. And then what about the length? So here are files that are generated. And yeah, you can reuse with any JPEG pair once you can't color, because you just need this, and this is specific to all JPEG pair. So you could reuse this for arbitrary pictures, set of pairs of pictures. You can set a predefined tag by using an extra block of the ciphertext for correction. So a file can tell in advance which tag will authenticate the decryption, even though the file itself is not known. It's not generated yet, which is exactly what we did by putting it inside our article. And also you can correct the authenticated data instead of the ciphertext. So this is our paper. And again, this works. And here our tag was dead beef cafe babe, because why not? So basically, an idea again of how it works. You take two files, you combine them with Mitra as a polyglot or an overlap polyglot if you want a nonce. These polyglots will be merged into a single file because Mitra also kept track of the offset where the contents switch, which you can, the key streams will be generated. This is XORed with the plain text to ciphertext, which will be sliced as a single ciphertext. This is done in parallel, and this is sliced from the swap offsets from Mitra. There will be correction of the correction, as in correcting the ciphertext so that it works with two different keys. And in the end, you get the right magic file that has all these weird properties. But again, all this operation will work silently. So we have several structure. Here are the logic of the several tools that we provided to do so. And we provide a lot of examples. I mean, again, this was also done so that the results are easy to reproduce. Even if you want to reproduce a computation, then we store the inverted tags, the inverted, and so on. You know, we just it's better for everyone. So basically, authenticated encryption is without key commitment is a security risk, and as you saw, Google, Facebook, and Amazon were vulnerable to in some ways. We also call that robustness rather than key commitment, but key commitment is a better word. I mean, and it's pretty Cool stuff because it's silent. Jason O'Connor. I'm gonna have to watch this one a couple of times. So good. Thanks. Yeah, yeah. To be honest, it's very nice because again, the vulnerabilities were known from the beginning, and if uh, so, basically there was nothing to do except that you can do a lot, and with the abilities of Mitra, you can really do that on a lot of file formats. You can do that with a lot of modes, and it's completely silent. It's not a bug, and with the authenticated encryption being verified, basically it's your payload has changed from one thing to the other, and that's like I mean, and it's not like it can be fixed very easily. You need to change the algorithm, but it's not like, oh, there's a bug here and just like a small overflow and you need to exploit. Crypto exploit this way via file construct is very nice because it's like it can cover a lot of files, and now Mitra is enabling us to just do that with a lot of file format pairs. As you saw, we provided a lot of examples. Again, all these combinations, there are probably more. And WASM PE, TAR, FLV, PSD, IRG. I'm not sure why. I mean, why not? Yeah, I mean, it's just to say it's not just two file formats. It's a lot more, and in different cases, in different very little situation. And again, they had this weakness from the beginning. Uh, so there are some solutions that are already exist, and our paper already suggests a few. Prepend zeros before the payload in the plain texts and check their presence after decryption. But some formats like ISO or DCOM naturally start with zeros, or store a hash of the keys, which was the workaround for the subscribe with Google um, bug. So lots of people were telling me for a long time that binary polyglots are boring and there's no point. But here, remember that our PDF article that is available online, you run OpenSSL twice on it, and it becomes a PDF viewer. And that could be something else. That could be WannaCry.exe or whatever. And it's not just CTR and GCM. GCM-SIV, which is the SIV one, is supposed to be more resistant. I mean, then do I have the GCM-SIV? Okay. And it's supposed to, yeah, mode of operation similar to GCM, as well as misuse resistant. So it's not for authentication, but how is it against authentication? Nothing is revealed, blah, 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 blah. Again, I'm not the best person for crypto. So just for not to for nonce resistance. But in the end, it still has this problem. And OCB3. And so they have some extra constraint, but there was still possible to do. But in this case, we didn't implement that in pure Python in Mitra directory, but in the key commitment folder. So OCB and SIV. The scripts are there. And will there be proper highlighting? Yes, there is. And the only difference in the constraints is that you need to align stuff to blocks, which is absolutely not a problem. If you want to payload to be aligned to blocks, just that's not a problem. And with OCB3, you need more blocks rather than just one block to correct. But 270 blocks, it's like for only 4 kilobytes, so it just grows your payload. You have an actual payload of another file, let's put it that way, but an extra 4 bytes per kilobyte parasite, that's nothing. But GCM SIV requires more time than GCM, okay? But it's also, this payload is relative to the file size. So basically, for SIV, we have examples, of course, and some of them we store them in both ways because it's not so. And some of them require some time of computing, a lot more time of computing. But in the end, the structure of the file, I mean, it's fairly different. Okay, no, they need more blocks, but that's about it. So just need the scripts, but this time the Sage script with the same output from Mitra, and that works. And we did with different kinds and whatever, just the examples are there. We really wanted to make a lot of stuff covered in advance so that to really raise the bar in terms of the abilities, like it's not just two file formats like the original fast message franking, or just BMP and JPEG. No, sorry, I said BMP and PNG earlier, but no, that was obviously BMP and JPEG. And what I want to say, I'm always losing this. So let's look at two files. So a PDF and executable. And as you see, the PDF, okay, so the MZ file, there's some garbage here, which comes from the result of encryption of PDF declaration. And here you see that it's not a very compact PDF declaration. Even I kept the non-ASCII bytes. It's a very, let's say, slow declaration. But even if this length change here, Mitra will keep track of where the offset is changing content, and this will be transparent as long as on the MZ side, the by offset to the P header will be preserved. So basically, Mitra knows that to do this operation on a P, you cannot go beyond 3C, offset 3C. So then we have the declaration. I mean, we have the whole P, right? And the whole P being encrypted with, so it's not encryption and decryption, right? It's encryption with one key and decryption with the other key. But the result is pretty random anyway. And then the content of the file is so transformed, not decrypted, but encrypted, decrypted. And then after that resumes the PDF content, except that we need two blocks to correct the ciphertext so that it matches the two keys. So yeah, that's basically what I just said. And there is alignment for the offsets for the payload at the end, which is not a problem. 14 bytes just after the end of file signature of a PDF is not a problem. The PDF is standard. The first object is a reference. There is a tiny appended data. The tiny appended data could be aligned if we put more data, for example, here to, if we wanted. So that's just this weird big object at the beginning. And the P is almost standard, except that the the DOS header is mostly overwritten, but it's usually not checked as long as it is, but it's not important for the execution under Windows. And the P pointer is preserved, and the rest of the P header is totally unmodified. Except that after the end of the P file, there is some encrypted stuff. So it's just a P with random looking appended data and a slightly corrupted DOS header. But again, a slightly corrupted DOS header, but not something with a very significant signature. And if you see this byte, you might. It's weird here, and then there will be some weird data, but the rest is all standard, the exact binary that you had initially. So again, did I introduce the JPEG thing? Yeah, I introduced the JPEG thing. I wanted to do that because why not? I mean, it's important. My Sumatra. Did I supply my Sumatra fixed? I hope so. Is it a mute? I'll explain why. This is Mitra GCM extra. Yes, my Sumatra is there. This is important because this Sumatra required a few tricks to make sure it's working. PDF piece with signature overlap, okay? And this works, and this is what I used in the paper. Why does it work? I think there was a write-up in Poker GTF for 19. Let's see. Write-ups. So basically, did I write it? Yeah, so basically, it is a PDF viewer, and PDF viewers contain PDF keywords. And being also, I wanted a Sumatra that is old enough, that is still compatible, but as small as possible, so that it's not doesn't bloat the file too much. And previous version were not good enough. Again, it's a single executable PDF viewer. So, and because it contains PDF keywords, it sometimes messes with PDF polyglots, which is understandable. Both contains the endstream keyword. So basically, it was compressed with UPX, except that I had to check to patch out some to patch out the some checks because shining the P header was interfering with the UPX depacking. So basically, there's a binary patch of a packed specific version of Sumatra, and now you can reuse it without any problem. That's this one. Okay, why not? So yeah, now it works. And JPEG P, no standard polyglot is possible. Of course, because there is an overlap of MZ and FFD8 signature. If you try with overlap, it will generate an overlapping polyglot. With verbose, it will give you all this output, and it will also give you some extra information. It's not a working polyglot without crypto. It gives you this file name, again, with the offsets where the content is switching size, and the byte to replace, and that's the MZ of the P signature. You generate a nonce, and it generates the whole file, and you can regenerate everything yourself. Now, JPEG. What can we done about JPEG? And it was a nice trick because, again, saving a few bytes. So we saw that for JPEG, you have FFD8 for the signature, FFFE for the command, and then the length of the command. So that's 6 bytes. And the longer the overlap, the longer the signature, the longer the brute force. So what can we do? So we have this. Okay, now we just add a parasite FFFE and then the length of the parasite, and then we can put whatever we want. So how many required bytes to control? It looks like we need 6. However, the length is big endian. So 5, if we round up the length to 1 more, then we make sure that the command is still good enough. But 4, if it will still generate a random length. We will not control that at all. But then maybe our parasites fits in a random length. And the thing is, even though this is random, we don't control the input, and this is a result of encryption, decryption, encryption with different keys, it still might not only be 64 kilobytes, which is not so good, not so big. So we can get a big speed up by trying our luck encrypting the PNG, the JPEG. I mean, doing crypto-polyglot with JPEG and only on 4 bytes rather than 6. So you just need, if you can try, and it's overlapping JPEG, and it's reducing the length to try to be random, and then it will just say there is a JPEG 4 fix to refix the value to so that it still works, even though we let the comment length being the victims of randomness. Do I feel lucky? Of course, you need to update the fixed file, which is generated by decrypt. It will generate another script, another file with just this 4 with some adjustments, and how this will work. Oh, the secret authenticated data was "My voice is my pass," which is from the Hackers movie, if I recall correctly, because it's authentication data, and in this movie, the authentication is the voice. Okay, so it works, and yeah, this is a reminder of the Mitra polyglot file name, and yeah. So, what do we cover? We cover crypto. We covered 2 ways that some aspects of cryptography can be enhanced by binary tricks, and I have to thank the people who introduced me to that, because without Stefan, without Daniel, without Sophie Schmick, without Jean-Philippe Masson, I would have no idea that that could be useful there. But you see, and again, Mitra didn't exist back then. It's when Daniel came and asked, "Can we generalize this?" And I was like, "What the hell is GCM?" And I was totally lost. I had I mean, yeah, you can know what the GCM is, but I remember Stefan actually needed to explain me what is possible, what is not possible, and then I'm writing hexadecimal on the whiteboard, and Stefan was also, "What's that?" And I said, "Oh wait, that's a JPEG signature." See what I mean? It was a very interesting, at least 9 hours of collaboration discussion, just to make sure we get things right, then scripting and so on. And I have to say that also the working with the where is it working to get the artifacts was very interesting, because suddenly our script were to be tested by people who have never used it, and that also helped us to improve the quality of our of our uh, of our scripts, of our artifacts, and so on. That was very, very interesting interaction, and really nice. And it's only then that I realized that, hey, we can reuse Mitra for the whole encryption thing, because at the time of the initial encryption, when was that? 2014, Whoa, that's some time ago. And now there is another joke that wasn't planned, is that I use to call this AES. That's Duke Nukem. That's the Skull and Crossbones. And AES in Russian is the acronym for nuclear power plant. So I remember it confused a few the Russian audience, where they were understanding this joke differently. So yeah, I hope you learned something. There are probably other cryptographic constructs that can be connected to Mitra or other tools. As you can see, there is no Mitra for hash collisions, and that's what I plan to do. Like, what about instantly collide all the file pairs together with something like Mitra, but a bit differently? And then Mark Stevens give us the computing power to do this all on SHA-1, on SHA-2. No, on SHA-1 is okay too. No, okay, I will just do it on MD5. Yeah, so I hope you had a good time. I see no questions. Um, and yes, thanks for your audience. Thanks for your attention. And yeah, I think I covered everything I wanted to say. Let's have a quick look. Yeah, if you're not familiar, this paper too. So this again, this authenticated contains a section of mine on the whole file formats, principles, parasites, appended data, and whatever. And this is the first time all this has been put into academic paper, appended, reappended. So basically, this paper is the academic counterpart of the Mitra presentation that I did. So basically, this is the if you are doing academic stuff and you want to basically use Mitra stuff and whatever. This is the original paper on it, even though it doesn't look like it's a paper of Mitra or about file format. But again, we the original paper was just on mixing two file formats, and this one is mixing a lot of them, and even with some very practical small examples. Not this paper, so that's a Usenix paper that is a bit shorter, but here actual examples on ambiguous HTML files. So now, yeah. Uh, Everything is in there. It was a great experiment, and yeah, now it covers a lot of stuff. And thanks again to Atul, Stefan, Sophie. I had very little interaction with Tai and Shai. And did I forget someone? Atul, Sophie, Stefan, and Daniel Bleichenbacher for inspiring it in the first place. I think he's being uh, yeah. The author would like to thanks. Oh yeah, Mark Stevens on Crypto-polyglots. Yeah, great stuff. Thanks a lot, everyone. And yeah, see you next stream. And yes, I hope you had a good time and have a good day, good evening, whatever. And see you next time. Bye bye, everyone.